what we're going to look at first are nozzles and diffusers. Okay, so the homework's only going to involve, it's actually going to involve a little bit of mass flow, but then nozzles and diffusers. Okay, so let's look at those right now. So we have nozzles, which constrict the area, and then you have diffusers, which make it bigger. Don't worry about the iPad. That was old stuff. Okay. What we're going to do is we're going to make some assumptions, okay, for nozzles and diffusers. Typically, these are the assumptions. If it's given in the problem that there's something, you're going to have to add it. So the biggest thing is we're going to assume Q is relatively small compared to delta H and delta KE of the fluid. Okay, because you have flow coming in and going out. So we pretty much neglect that. There's no mechanical work, so W is 0. And we pick points that are at the same datum. Okay, so right center line of the nozzle or diffuser. So there's no change in potential for the fluid. Okay. In your homework, though, I want you to show this green box equation, then get down to there. Okay. Later on, after this chapter, you can then use, okay, here's a nozzle, here's a shortcut equation, get the numbers. Okay. Hopefully you're starting to see how we build everything. It's all based on energy, right? We'll get to efficiencies more, too, after this chapter. Okay, talk about efficiencies of cycles and how they work. So does everyone understand these would be our assumptions and how it helps us reduce this first law down to that? So I'm going to do an example here in a minute on a nozzle. So I'll bring up the problem here. Okay, so the diffuser in a jet engine is designed to decrease the kinetic energy of air entering the engine compressor without any work or heat. Calculate the velocity of the exit of the diffuser when air at 100 kilopascals and 30 degrees C enters it with a velocity of 350 and exits at 290 degrees C. Okay. So why don't you set this problem up, write the first law, and we'll go from there, okay? So I'll make a nice sketch here. So diffusers. And again, if you have questions, please ask. Comes in. Goes out. And P1. Yep. Yep. Diffusers are just a little too big. Yep. P1 was enters. So 100 kilopascals. T1 is 30 degrees C. P2 is 200 kilopascals. T2 is 90 degrees C. What are we using for our working fluid? Air. Are there tables for air? The only things you're going to get for air are R, CB, and CP, right? So it's a gas, right? So you probably will hopefully think, okay, we can use CP delta T somewhere probably. We're going to find V2. And I'm going to cheat. I'm taking the easy way out. And if you have this and you want to do this, if you have a tablet, sure. by all means. Yep. You can definitely do that if you want to. Yeah, I'll allow it. Yeah. There's my assumptions. Oh my God. All right, so we have assumptions.
Wait, what
We have our first law.
Really
That means whatever
constant flow, right?
whatever comes in must equal going out. Yep.
Oh.
Think about it in your water tub. That water never changes height.
Okay.
That's what that means.
You could have a closed
We're not gonna
system
deal with
stand,
something that's
but an
not
open
steady.
system stand.
You can, sure. Yep. All right, we got the first law. We did our assumptions. And what can we switch delta H to? CP T1 minus T2. And CP is 1.007 kilojoules per kilogram K. So now you're going to start using and look up CP values. Try not to get that confused with CV. People do that all the time. Okay. And you end up getting V2 to be 40.7 meters per second. Oh, we also could add what to the assumptions? Ideal gas?
Oh.
And what is the Q? What does that one mean when you assume it's 0? What can you say that type of system is? Not really. Because temperatures in and out could change of the nozzle. But if I say it's insulated, Q is 0, but that's also called adiabatic. Thank you. Yes. Anybody else think of that?